Greetings. In the previous video, we managed to define the problem and also find the properties. We are now in a very good position to simplify the conservation equations for this problem. Now, let's start with simplifying the conservation equations. The equations are as we have them here. You see, this is the mass conservation law, and this is the first law of thermodynamics. And what we want to do is to simplify these equations for the control volume or control volumes that we specify. Now, look, we have four control volumes, in fact. One is control volume, which is the whatever there is in A. The second one is control volume B, and that contains whatever there is in B. This one is the valve, and that is one control volume. And there is another control volume, which although I have drawn it fairly large, but really what I mean is that this control volume is the water that is inside A plus B. So if I want to draw it in a more clear manner, I should just draw it in green, and it is whatever that goes through here, and it is that one in B. I mean, this control volume is decided such that it does work outside. See, if you draw the control volume here, it doesn't show that there is work that is happening outside. But here we have a control volume that actually has A and B, the water in A and B inside it, and does work on the outside. So now, just to write these two equations, I have them very small under my picture, and just to write the equations and simplify them for these different control volumes, let's start with A. And for control volume A, the mass conservation law tells us that M2 minus M1 equals, there's no mass that enters, but there's mass that exits. So this equals minus ME. And that's how we simplify the mass conservation law. Next is the energy conservation, and ignoring all the effects of change in velocity and height and elevation, which, well, we can do in this problem, it ends up with M2 U2 minus M1 U1, and that is the change of energy, the final energy minus the initial energy is equals, it is one term that the energy that enters with the mass that enters, no mass enters, so no energy enters, mass exits, so minus ME HE, and also there is heat transfer from A, so plus QA, and there is no work. That A is a solid tank with solid boundaries, and there is no work through it. So these are the first two equations in for A. Now, next is B. Let's do it with B. For B, we have M2 minus M1 equals to be mass enters, so it is Mi, but nothing exits, so it is only Mi. Note that it's good if I add an A to all subscripts, just to make it clear that I'm talking about A and not anything else. The other point that I have to make is that this point is E, this point is E, and this point is I. Although this subscript would not easily go with the valve because it is denoting valve entry as E and that exit as I, but still we have to, we just make it clear what we are saying, and that would do. So if we are putting here E, when we write our equations for the valve, still this would be E, and this point would be I. Now, the energy equation for B would be, this is B, this is B, and this is B. This is M2B U2B minus M1B U1B equals mass enters B, and so it brings energy with it, IB times HIB plus some work, some heat transfer, QB, and also there is some work because there is a piston that moves. So this is the work done by B. So we have both QA and QB. Okay. Now the next set of equations you may write are for the valve. And as for the valve, we may again, you see the valve initially has no mass in it, and finally also has no mass in it. So no mass is stored in the valve, and therefore M2 or M1 are both 0. And for the valve, we denote it by V, ME 0 equals the entering mass, which is ME, minus the exit mass, which is MI. Both are for V. It would be as good if we don't place any of V here, because if we don't use A and B and E and I, then I and E would be both A and valve and B and valve would share the subscript. So A and valve would share the subscript E, and B and valve would share the subscript I. But as it is, 0 would be MEV HEV minus, that is the entry energy to the mass, minus MIV HIV, that is the exit energy from the valve, and the valve has no heat transfer and no work. So it remains just like this. Now, the last system, in fact, here it is system, Uh, these are all three were control volumes, but this last one is a system because no mass leaves A plus B. So A plus B plus V is now our system, and what we write for it is that the mass conservation law tells us that M2A plus M2B minus M1A plus M1B equals no mass enters, no mass leaves, and therefore this is 0. You see, no mass enters the whole control system and no mass leaves it. It's a system. A plus B together, there's no exchange of mass to the outside. Now, as for energy, M2A, M2A, U2A plus M2B, U2B, which is the final energy of both A and B added together minus M1A U1A plus M1B U1B, which is the initial energy of A and B added together, equals Q A plus B minus W only B, because A does no work. So here we have four sets of equations that we could write, and there are some knowns in it and some unknowns in it. We have to here discuss. We are now in a good position to put numbers into these equations and see which values do we have and which values should we calculate. Now, for A, we know that M2A equals V2A divided by V2A minus, and replace M1A with V1A, which of course these two values are equal, divided by V1A, and that equals minus MEA. And what we know here is that we could give values. Here, this is 0.15 divided by 0.749 and minus 0.15 divided by 0.00119. This ratio, the first ratio, is the final mass in A, which is equal 0.2 kilograms, and this ratio is the initial mass in A, which equals 126.05 kilograms, and therefore subtracting these two values, which gives us that MEA equals 125.05 0.85 kilograms. So we now know how much mass has gone out of A, and this is exactly the same mass, the mass that has gone out of A, and this is exactly the same mass that has entered B. MIB would be exactly the same, and also the mass that goes through the valve is also the same. So we know quite a number of items. Now, the first law of thermodynamics for A may be written as we have quite a number of values here. In fact, the only unknown are is QA, and they have to make an assumption for HEA, and we shall explain it right away. So M2A is 0.2 times U2A, which is 2682.3 minus M1A U1A, which is 126.05 times U1A, which is 940.88, and that equals ME, okay, MEA, which is minus 125.85, so 125.85, and times HEA, which is the enthalpy of the mass that leaves A, and plus QA. It is quite common to assume that HEA is the average of the enthalpy at 1 and the enthalpy at 2. We have two conditions. These are our two conditions, initial and final. H1, initially, the mass in A has enthalpy 943, and finally it has enthalpy 2906.9. A fairly good assumption is to take an average. Sometimes when this won't be as good an assumption for B, because as for B, the distance between the initial and final is just too large. There's nothing initially in B, and therefore that enthalpy would be 0, and the distance would be, and the final enthalpy is 2909, which is quite high. For such a distance, an average would not produce a good result. But for and even this one is fairly high. I solved you some problems where I could calculate and compare the a sort of average calculated from the first law with the average that is just the average between initial and final points. In this problem, we don't have such options, so the best assumption for whatever that is leaving is just to take an average between these two values. So what I do is to calculate HEA as H1A plus H2A divided by 2. This would be 943.64 plus 2906.9 and divided by 2, and that makes HEA to be 1925.27 kilojoules per kilogram. And inserting this value into the equation for the first one, for A, would result QA, heat transfer from A to B, 130,009.575 kilojoules. So that is the heat transfer from A, or better say into A, since this has a positive value. I mean, uh, let's see that there is energy leaving A, and therefore to keep the temperature constant, A should be heated, and the heat A requires, this is QA, and the heat it requires to keep the temperature constant is just this value. This is QA. Well, we are now done with both mass conservation and energy equation for A. I would move to B, to the valve, um, because it's very easy to handle it. We all have all properties at E, and we could also calculate all properties for I. It means that you see the mass MEV equals MIV, therefore MIV, which is the mass leaving the valve, is 125.85 kilograms, and with these two masses equal and canceling out, we would have HIV equal 1925.27 kilojoules per kilograms, which is the assumption for uh, a diabatic, no work. Of course, there's no work on the adiabatic valve. You see, this value, if we were to average the incoming enthalpies initially and finally for B, then first there is nothing in it. So um, HIV HIV average would be 0 plus 2909.0 divided by 2, and this would equal 1455.5 kilojoules per kilogram, which is different with this 1925, as just they are both assumptions and approximations, but I would trust this approximation more than I would trust this one, because 1925 is just an assumption for a adiabatic valve, which is a fairly good assumption at this stage. We don't have any further knowledge about what's happening inside uh, the valve, or at its inlet or outlet. But I shall later on show you that. You see, our assumption for HEV decided on Q here. Okay. Now, the assumption that equals these two values, enthalpies at inlet and exit to the valve, and decides on the inlet enthalpy to cylinder B, will decide on the heat transfer to the B. Now, if these two values, if these two heat transfers are added, this would make the total heat transfer. As we shall see later on, whatever assumption we make here, eventually the process here would cancel out and the total heat transfer would be the same regardless of this assumption that we make. So by this assumption, in fact, we are dividing the total heat transfer to A and B. And this is just the type of the best guess that we can make anyway. This is the best guess. So what we have here is that we now know whatever that enters B. We know B's initial condition, we know B's final condition, and this would place us in a good position to calculate the heat transfer from B. One point that we don't know is the work that is done through B, and we shall now calculate that as well. And I shall continue the rest of the solution in part 3. Cheers.